Okay, so now we're going to talk about something called buffers. So what a buffer is it's a solution that has the ability to resist change in pH, and the way it's able to do this is because it's made up of both acidic and basic components. So first let's just define what a buffer is, and then we'll talk about it and do some calculations. So it's a solution characterized by its ability to resist change in pH. And the way it's able to do this is because it's made up of both acidic and basic components. So specifically, it's made up of a weak acid and its conjugate base. Or a weak base and its conjugate acid. So it can't just be any acid and base to make a buffer. It has to be a weak acid and its conjugate base, or a weak base and its conjugate acid. That is how you make a buffer. And sometimes you'll see this called a buffering system. And usually you'll have one either acid or base, and then the conjugate of that acid or base would be in a salt. So for example, a buffering system would be maybe hydrofluoric acid, and sodium fluoride. So hydrofluoric acid, HF, this is a weak acid. And sodium fluoride, NaF, we know this sodium is neutral because it's the conjugate of a strong base. And this fluoride ion is conjugate base of hydrofluoric acid. So this would be an example of a buffering system. A buffer could be made up of a solution that contains both hydrofluoric acid and sodium fluoride. So if we had a beaker and it had a solution in it of this buffering system, so you have, let's say, you have hydrofluoric acid in here, and you have the fluoride ion in here. I'm not including the sodium with the sodium fluoride because we know this salt is going to break apart into sodium and fluoride. The sodium does not affect the pH, so I'm just showing what is going to actually be reacting to affect the pH, which in this system is the hydrogen fluoride, hydrofluoric acid, and then the fluoride ion. So what happens when you have a buffering system like this is if you add an acid, if you added an acid to this, the acid will be neutralized by the weak base, the fluoride ion. If you were to add a base, the base will be neutralized by the weak acid, hydrofluoric acid, or hydrogen fluoride. So this is how a buffering system works. buffers all have what's called a buffering capacity, meaning you could overwhelm this system where you could definitely add so much acid that there's not enough fluoride to neutralize it and then the pH would change. Or you could add so much base that it could overwhelm the hydrofluoric acid and then that would change the pH. But within what's called a buffering range, and we're going to talk more about buffering capacity and buffering range and all of that a little bit later, but well, maybe we'll just talk about it now. So usually a buffering system has what's called a pKa. So just like the pH is the negative log of the hydronium ion concentration, the pKa is the negative log of the Ka. So you would have the Ka of this case in hydrofluoric acid. You would take the negative log of the Ka, and that would give you the pKa. So we're going to do more examples of this later, but just for right now, let's say the pKa of the Ka of hydrofluoric acid is 6.8 times 10 to the negative fourth. So let's say what the pKa would be. The pKa would be the negative log of 6.8 times 10 to the negative fourth. Same thing, same rule. When you're taking the log of something, the number of significant figures in that value is the number of decimal places in your log. So I would say the negative log of 6.8 times 10 to the negative fourth is 3.167. I'm going to say 3.17. That's the pKa of hydrofluoric acid. So usually a buffering capacity, and this is just a rough estimate, but usually the buffering capacity is plus or minus 1 pH unit. So that is just a rough estimate. So that means that if you had a buffering system of hydrofluoric acid and sodium fluoride, it would do a good job of resisting change in pH from about a pH of 2.17 to about a pH of 4.17. Once you get outside of this range, this buffer would no longer be effective. So depending on what kind of pH you would want, for example, many chemical reactions have to be held to within a specific pH, so that chemical reaction would be done within a buffering system. All biochemistry, all of the chemical reactions that are happening in our bodies and in our cells happen within a very small window of pH. And all living things, all living systems are maintained by buffers. Our blood, for example, is maintained by the carbonic acid buffering system. And your blood pH has a very small window in which it must exist for systems and enzymes to all work correctly. So we talk a lot more about physiological systems and biochemistry. In this class, we'll talk about buffers and just kind of explaining the chemistry that's happening, the reactions that are happening, how the acid can neutralize the base, and how the basic component can neutralize the acid. We'll do a lot of examples and calculations with buffers. We'll draw some curves, seeing the kind of buffering range or buffering capacity. But big picture, a buffer is something that has the ability to resist change in pH because it's made up of a weak acid and its conjugate base, and usually that conjugate base is contained in a salt, or a weak base and its conjugate acid. And again, the conjugate acid would be contained in the salt.